Welcome to Lecture 6. In this lecture, we'll cover key concepts in mathematical economics, starting with straight lines in economics, the consumption function, and more complex nonlinear functions like exponential and square root functions. Straight lines. In economics, we often express relationships between variables using straight lines or linear equations. For instance, consider the equation y equals 2 times x plus 1. In this equation, x is the independent variable, y is the dependent variable. This means that y is a function of x, which means that y changes as x changes. The equation is linear because it graphs as a straight line. The slope of the graph is 2. This means that for each 1 unit increase in xy increases by 2. The intercept is the value of y when x equals 0. In this case, when x equals 0, the value of y is 1. So the line intercepts the y-axis at the point 0, 1. The general form of a linear equation is y equals m times x plus c. Here, m is the slope and c is the intercept. These are called parameters. The parameters can be adjusted to alter the relationship between x and y. Look at the graph here that illustrates y equals 3 times x plus 2. As you can see, changing the slope, 3, and intercept, 2, changes the steepness and position of the line. The consumption function. Now, let's introduce the consumption function. This is a linear function used to model the relationship between consumption and income in an economy. The equation for the consumption function is c equals c0 plus c times y. In this model, c represents total consumption, y represents total income, GDP, c0 is the autonomous consumption, c is the marginal propensity to consume, MPC. c0, autonomous consumption, represents consumption that happens regardless of income. For example, it could be basic consumption from government transfers or loans. C1, the marginal propensity to consume, represents how much of each additional unit of income is spent on consumption. This model shows us how consumption increases as income increases, and it helps policymakers predict how changes in income levels might affect overall consumption. Bendy lines, nonlinear relationships. However, not all economic relationships can be represented by straight lines. Most relationships are nonlinear. This means that the relationship between variables isn't constant and changes over time. For example, consider a growth function. Growth is often an exponential process, meaning that as something grows, it speeds up over time. This kind of relationship is represented using an exponential function. Another common nonlinear function is the quadratic function, such as y equals x squared. In this function, the slope of the graph gets steeper as x increases. The relationship between x and y accelerates over time, which is common in many economic phenomena like investment returns or technological progress. Opposites. Decreasing slope. In contrast to functions with increasing slopes, some functions have slopes that become less steep over time. These functions represent cases where the rate of increase is falling. One example of this is diminishing marginal utility. As you consume more of a good, the additional satisfaction, or utility, you gain from consuming each extra unit decreases. This is often represented by a square root function. For example, u equals the square root of x. In this function, as x increases, representing the amount of a good consumed, utility increases, but the rate of increase slows down. This concept is fundamental to understanding consumer behavior and is used in modeling utility and production functions. Final notes and tutorials. Before we conclude, I want to encourage you to look at the tutorials that has been uploaded. These tutorials will provide further practice and examples to help solidify your understanding of these mathematical concepts. We'll dive deeper into real-world applications and provide exercises that will help you better grasp how these models work in practice. Thank you for attending today's lecture. We've covered the basics of linear and nonlinear functions, including their application in economic theory and their relevance to real-world policymaking. I look forward to seeing you in the next lecture, where we'll continue exploring these topics in greater detail.